Welcome to the lecture System Theory 2. This first module is about a little bit about the content of the class, what we are going to cover through the semester, a little bit of organizational information, and briefly let me introduce also the Institute of Automation of Complex Power System that is in charge of this class. So the Institute of Automation of Complex Power System is part of the E.ON Energy Research Center. The Energy Research Center was created in June 2006 as a cooperation between RWTH Aachen and the company E.ON. At the beginning, we had 5 chairs involved in the center, coming from 4 different faculties, and in that respect was a big experiment for the university to bring 4 faculties together and actually in one building. And the topics of our research were mostly energy efficiency, sustainable energy supply, and specifically in the center, the Institute of Automation of Complex Power System is one of the institute covering electrical engineering topics. This institute was founded in 2008, so 2 years later after the beginning of the center. We currently have also another professor apart from me, Professor Ponci, and also a visiting professor from Hungary, Professor Reis. We are organized with a chief engineer and 8 postdocs and a large number, more than 40 research assistants, many of them involved also in the preparation of this class. We also have a group of software developers so that any automation solution is professionally developed before implementation. And we welcome students to cooperate with us as HIVI or in master project. Last but not least, we have a staff supporting for the administration and the secretariat. Topic-wise, the institute is built on 2 main pillars, more related to energy systems. So the dynamics of grid operation, which means understanding the topics of grid stability and grid dynamics, and looking at hybrid DC and AC grids, looking at the automation and monitoring of grids, and the critical topic today of integration of renewables. On a side, together, what makes us different, we have clear IT competence in the group of ICT for Energy. These are scientists that came in the institute from the previous Lehrstuhl für Betriebssysteme, so Institute for Operating Systems, and they allow us to have experience in energy as data-driven system, distributed computing, high-performance computing, cloud application. Together, thanks to these 2 pillars, we cover topics in application like smart cities, smart grids, flexible electrical networks with specific focus on DC, medium voltage. We are part of the center with wind power drives, and we've been doing projects in the area of future internet. That's, I think, what I want to tell you about the institute. You're welcome to visit our website for more information, to look at the project we are doing. Now, getting more specifically to System Theory 2, everything that we deliver as material will be available on Moodle, where you can find the slides, additional reading material. You can find the exercise, some of the exercise with solutions, and all the organizational information that may be of interest for you. We have a specific email address to contact the team working on the preparation of this class, as you see here in the slide, ACS Teaching SIS2 at eonnrc@wthaachen.de. And now let me start with the content. In a very nutshell, very simple, the class covers digital control systems, more precisely hybrid systems. We'll see in the first lecture immediately while we talk about hybrid system. And then a second big element of the class are system represented and controlled in the state space. Getting more in details and talk about the specific of the first lecture, the first module, we start with the introduction to linear discrete time systems, which means entering the topic of digital control. We review some of the fundamental digital signal processing like sampling, Shannon theorem, and how you convert information from analog to digital and digital to analog, so the role of sample and hold and their representation, which allow us to build the mathematical foundation of digital control systems, and looking at the representation of discrete system using difference equation, looking at the impulse response sequence in discrete time, the representation as convolution system, and the mathematical description of the sampling process. The lecture 2 allows us to introduce the frequency domain response. We will talk about the Z transform. That's the equivalent of the S transform or Laplace transform in the continuous time domain. We will look at the property, how you perform the inverse of this transformation, and how you can compute the Z transform of systems that are originally defined in continuous time. With this knowledge, both in the time and frequency domain for discrete time system, we can tackle the analysis of stability of linear discrete time systems. We start with an introduction to the definition, and then looking at the mathematics that we were able to define in the first 2 lectures, we were able to define the criteria for stability. We'll compare a set of them, and the relation between the poles in the continuous and discrete times, so that we can better understand the relation between system in continuous time and discrete one. In the lecture 4, now that we know the criteria for stability, we can start with the first example of digital control algorithms and their design. We start first of all with the mapping of classical control structure like PI and PID in the discrete time systems. And then we look at the design of discrete time compensation algorithm. But here already we start with something that is specific of discrete time systems, so introducing the design of control as deadbeat control, which is a technology, a solution that is only possible in discrete times. With lecture 5, we jump in the other big pillar of the class, which is the state space representation. All the topics in the state space will be considered both for continuous time and discrete time. This way we complement everything you have done in system theory 1 with the state space domain. So the first system theory class is mostly based on the input-output descriptions, while here the focus is on the representation as state space. So we start with the definition of state, the solution of the state equation in the time domain, and the important topic of state transition metrics, and one of the most important theorem for the state space representation, which is the Cayley-Hamilton theorem. In the lecture 6, we look at the so-called canonical form. As we will see, there are many options in selecting the state variables, but there are some that have specific properties. So they bring a specific structure for the state space representation. These are called canonical form. We'll have the controllable canonical form and the observable canonical form. And last but not least, the Jordan form. But because we have several options, we also have to introduce how to move from one representation to another one. So talking about similarity transformation and the possibility to transform from one representation to another with specific focus to the diagonal form. The lecture 7 look at the controllability criterion, so how we assess that a system is controllable, which is a very important property for both continuous and discrete time system, but also observable. Obviously, there is a link with the previous canonical form defined in the previous lectures, but here we understand how a generic system can be defined as controllable or observable. With all these tools available, it's now becoming possible in the lecture 8 to talk about the structure and the synthesis of control in the state space domain. So we introduced the idea of feedback in the state vectors, which is the main architecture used in the state space representation for control design. And then we look at specific method of design that can be applied to calculate the values and the coefficients involved in this feedback line. This is, for example, the pole placement method. And as said before, we will look at this both in continuous and discrete time space. That was about control, but as we will learn many times, we need to enhance the information we have for measurement with an observer, which allows us to reconstruct the internal information. So exactly that's the state representing the system, and then we need the so-called observer. We'll define what an observer is. We will calculate how this can be implemented, so there is the design processes possible for observer. And at the end, this will bring us to a specific type of observer, which is the topic of lecture 10, which is the Kalman filter, which is a stochastic type of observer that is a result of a process of optimization, minimizing the uncertainty in the observer process. I'd like to keep always one module free at the end to perform a review of the topic of the semester, so that we browse quickly again the topic when these labels now have a meaning, different from right now that I only had the possibility to introduce a lot of terminology, but for you many times maybe a little bit abstract. But at the end of the class we will review this with the knowledge that we got through the semester, and this will be also good to maybe stimulate questions from your side in preparation for the exam. We identify some good literature of reference. The terminology we use through the semester comes from one book, the Unbehauen, Rechnungstechnik 2. This is the book that was used to prepare the slides and for all the terminology and symbols we use. There are additional references that are listed here in the slide in case you want to get more of what we can provide you with our slides and the lectures. And also some reference of continuous time systems are also here provided. One thing we introduced from the first semester is the idea of a practical project. This practical project allows you to get some direct experience on control systems. So the class control system theory is traditionally quite mathematically oriented, and what is difficult many times for the students to grasp the link to reality. The idea of the project is to give an hands-on application where you can test your knowledge. We will distribute the hardware, so it's a real system to be controlled. It's basically an inverted pendulum that will be used. What we ask you is to perform the design of the controller and then to write a report with your outcome. If the project works, so it's completed successfully, that will allow you to boost your grade. So the project cannot be used to pass the exam, but once you pass the exam, you can use this as a bonus to enhance of a bonus of 0.3 your grade. So the pendulum is something like reported here in this short video, where you can see the inverted pendulum that is controlled by an Arduino microcontroller. The design and the implementation can be done simply using MATLAB Simulink. Then you download to the Arduino, and hopefully, as in the video, you will be able to build a system that is able to compensate for disturbances. So in this case, somebody hitting the pendulum with a hand and try to bring it back to the original position. The idea is that you will use the knowledge learned in the semester to perform the complete design from the specification to the implementation in the real-time systems running in the Arduino, and I hope this will bring you a more concrete understanding, more practical understanding of the topic we will be discussing through the semester. With that, I would like to complete my introductory class, and I thank you for your attention, and we'll continue in the next module.